In this video, I will show how to quickly build a concept model of a chilled water system. We will start with a simple schematic layout, then move to 3D modeling of the building and equipment. First, I want to show schematically how our chilled water system looks. I start by drawing a chilled water tank, which is used to accumulate a larger amount of water in the system and help stabilize the operation. The equipment I draw is shown in green, and the pipelines are represented with red lines. A typical chilled water system has two main loops. The first loop connects the chillers, where the water is cooled. The second loop goes to the users, meaning the equipment or processes that require cooling. The chillers remove heat from the water, and the chilled water is then circulated through the user loop to absorb heat from the equipment before returning back to the system. For this example, I place 3 chillers and 4 users. Pumps are not shown in this schematic, but they will be located in the user loop to circulate the chilled water through the system. In this video, I draw only the equipment and main pipelines. In the next video, I will detail the system, adding valves and other required components. We will also discuss pipe diameters, water flow velocity, and system capacity. This configuration allows the chillers and the users to operate more independently, while the tank acts as a hydraulic buffer between the two loops. In a real installation, this layout also makes it easier to add or remove chillers or users without disturbing the whole system. Let's move to the modeling phase. As an engineer, I do not like to model objects hanging in space, so first I will create a simple structural base for the system. I will add a few grid axes and columns to represent a small building, so the equipment has a clear and realistic location in the model. That already gives us a better understanding of the layout and the available space. Let's assume the building has 400 by 400 millimeters reinforced concrete columns. I place them along the grid axis to define the building frame and available space for the chilled water system. Our building is 18 by 18 meters with a height of 6 meters. That gives enough space for the tank, chillers, piping, and maintenance access around the equipment. Along the perimeter, I add 200 millimeter thick walls, plus one internal wall to divide the space. For the internal wall, the exact position often depends on the wall type. If the wall is made from sandwich panels, it is usually placed next to the columns because structural beams typically run between the columns and the panels can be fixed directly to the frame. Sometimes the wall can also be installed between the columns, depending on the building structure and the layout requirements. And I leave 2 gates, each 4 meters wide, so equipment can be brought inside. Our building skeleton is done, so now we can move on to the equipment and start adding some tanks. Since the building free height is 6 meters, I choose a vertical chilled water tank with 2 meters diameter and 4 meters height. A vertical tank helps with better separation of water temperatures. Colder water stays in the lower part of the tank, while the warmer return water accumulates higher, which reduces mixing and improves system stability. Buffer tanks are used to increase the water volume in the system. This helps stabilize the operation of the chillers and prevents them from starting and stopping too frequently. They also smooth temperature fluctuations and make it easier to balance the flow between the chiller loop and the user loop. In many systems, the buffer tank also acts as a hydraulic separator, allowing the chillers and the user side to operate with slightly different flow conditions. Our system also needs circulation pumps. I place them in the user loop because this is the part of the system that distributes chilled water to the cooling users. On the chiller side, separate pumps are not always needed, since chillers often already have internal pumps. Because of that, in this model, I do not add extra pumps to the chiller loop. Now I add some equipment that will need cooling. The first one is a shell and tube heat exchanger. The second and third are 2-plate heat exchangers, which are also very widely used in chilled water systems. And the last one is a reactor-type vessel, just as another example of equipment that may require cooling. This gives us a more realistic user loop with different types of cooling consumers connected to the same system. Next, I need to add the water nozzles to the buffer tank. In this case, I use DN200 nozzles with PN10 pressure class because the system operating pressure is around 4 bars. That is enough for this chilled water application and fits this model well. Since warmer water is less dense, it naturally rises to the top of the tank, while colder water is denser and sinks to the bottom. Because of this natural stratification, the return water from the users, which is warmer, is connected to the top of the buffer tank, and the cold supply water is taken from the bottom. So in this model, I place the nozzles at the top and at the bottom of the tank to follow this flow pattern and keep the temperature layers inside the tank as stable as possible. In the next video, we will detail the tank further, adding level indicators, connections, and other required equipment needed for proper operation. Here I have already drawn the DN200 loop to the users. To support this pipeline, I will use the building columns and add some steel profiles for pipe supports. In other cases, the piping can also be suspended from the roof structure using hangers if the building design allows it. The chilled water is distributed through a loop. One advantage of this layout is flexibility. Equipment can be connected at different points along the loop, so new users can be added later without redesigning the whole system. When designing the piping, it is also important to consider possible future expansion. If additional cooling equipment may be installed later, the pipe diameters should be selected with some reserve capacity. This way the system can handle larger water flow rates in the future without needing to replace the main pipelines. For chilled water systems, several pipe materials can be used. In many industrial installations, carbon steel pipes are commonly used because they are strong, reliable, and suitable for larger diameters like the DN200 loop shown here. In some cases, stainless steel can be used, especially where corrosion resistance is important. For smaller systems or building HVAC installations, plastic pipes such as HDPE, PPR, or PVC are also widely used. The final material choice usually depends on factors like system pressure, temperature, corrosion conditions, installation cost, and pipe diameter. The loop is now ready, but I will relocate the pumps to create a better maintenance area and overall layout. Even though the system is circular, the pump position still matters. The pump suction side should take water from the buffer tank, where the chilled water is available for circulation. The pump discharge side should go toward the users, because the pump's job is to push the chilled water through the system and overcome the hydraulic resistance of the piping, valves, and equipment. While relocating the pumps, I noticed the space was getting tight for proper installation and maintenance. So I extend the building by another 6 meters to create more room for the pumps and piping layout. Now I will create the chillers themselves. At this stage, I just use large boxes as simple placeholders. Later, I will add the nozzles and other details. I place the chillers outside the building because they need a good air supply and airflow around them for heat rejection. I leave about 2 meters of space from the building wall and from other chillers. This gives enough room for the chiller loop piping and also provides a walkway for access and maintenance around the equipment. The principle of this loop is the same as for the user loop. Water circulates through the chillers, where heat is removed and then returns back to the buffer tank. Now let's quickly add the nozzles. The nozzle size will be smaller than the main loop. For the chillers, I use DN100 nozzles. Let's move all the chillers a bit to the left side, so the loop can connect to them in a cleaner and more practical way. When I model something, I often have to move equipment around several times until I find the best position. At the beginning, the layout is usually only approximate. As piping is added, it becomes clearer how much space the pipes need, where supports will be placed, and how maintenance access will work. Because of that, equipment often needs to be shifted, rotated, or spaced differently so the piping runs more naturally and the layout stays practical to build and maintain. I already started creating the nozzles on the tank. They are the same size as before, DN200, just rotated toward the chiller side. This position should work well for connecting the chiller loop piping. Now I create a simple loop for the chillers. I think I will adjust the nozzle heights on the tank slightly to improve the water flow pattern. A chiller removes heat from the water using a refrigeration cycle. Inside the chiller, refrigerant evaporates in the evaporator, absorbing heat from the chilled water. This cools the water that circulates through the system. The refrigerant is then compressed, and the heat it absorbed is rejected to the surrounding air through the condenser. After that, the refrigerant expands and the cycle repeats. So the chiller continuously takes heat from the chilled water loop and releases it to the outside environment, keeping the system water cold. I start connecting the chiller nozzles to the main pipe. One important note: when working with a real chiller, it is very important to carefully check where the inlet and outlet connections are located. Different manufacturers may place them differently, so it's easy to mix them up during modeling. To avoid mistakes, I usually add small notes next to the nozzles to clearly mark which connection is inlet and which is outlet. In our situation, I simply raise the chiller nozzles up to the level of the loop so the pipes can connect easily. If you are working with real chillers, it might be the other way around. You may need to adjust the loop elevation to match the actual nozzle heights on the equipment. And this is how our chiller loop looks now. At the ends of the loop, I can also place caps to close the pipeline. Now we can connect the user pipes with the pumps in the tank. For the pump discharge nozzle, I make it one size smaller than the main loop. Since the loop is DN200, the pump discharge will be DN150. On the suction side, I use a larger pipe, DN250, connected to the tank nozzle DN200. A larger suction line helps reduce velocity and pressure losses, which improves the pump suction conditions and reduces the risk of cavitation. Near the pump connections, it is common to install flexible connections. These are short, flexible sections that help absorb vibration from the pump and prevent it from transferring into the piping system. They also allow for small alignment differences between the pump and the pipeline, which makes installation easier and reduces mechanical stress on the equipment. At this modeling stage, I'm simply trying to connect everything together. Later, we may find better piping routes, especially around the pumps and the tank. In my experience, the best layout often appears only after moving equipment several times, sometimes even after the third relocation. In this layout, the pumps take water directly from the buffer tank. The tank acts as a stable water source, so the pumps always have a consistent supply of water, which helps maintain reliable operation. The buffer tank also helps separate the chiller loop from the user loop hydraulically. This means the flow rate in the chillers does not have to be exactly the same as the flow rate in the user loop, which makes system operation more flexible. Another benefit of the buffer tank is system stability. Without enough water volume, chillers may start and stop too frequently, which reduces efficiency and increases wear. The buffer tank adds thermal mass, allowing the system to operate more smoothly. In the next video, we can move from the concept model to a more realistic design. There we can make the main calculations, select real equipment from the internet, define the required flow rates, and then adjust the pipe sizes, pumps, and buffer tank volume accordingly. Also pay attention to the pump nozzles and nearby piping. Both the suction and discharge pipes should be properly supported close to the pump nozzles, so the pump is not loaded by the weight of the piping or by thermal and mechanical stresses. On the discharge side, I also avoid making one long straight pipe directly into the nozzle. Adding a change in direction helps create a more practical layout and avoids putting unnecessary stress on the pump connection. I also like to arrange the pipes one above another. It makes the layout cleaner, the support simpler, and the whole piping system easier to understand. I try to avoid strange angles and unnecessary turns, so the routing stays ordered and more practical to build. And finally, I make the last connection back to the tank, closing the loop. Let's quickly connect the users to the user loop so we have a complete principal view of the system. So this is our basic chilled water system model. In the next video, we will calculate flow rates and select real equipment. Thanks for watching, and don't forget to subscribe for more engineering content.